Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts, and fall asleep to the sound of discovery. The edge of the universe. Close your eyes and imagine standing at the shore of an endless ocean, where waves of starlight wash against the boundaries of everything that exists. Tonight, we journey together to the most distant frontier imaginable, a place so far away that light itself grows weary in the traveling, a realm where space and time begin to lose their meaning, and where the universe shows us both its birth and perhaps hints at its end. This is the edge of the universe, the final horizon beyond which our telescopes cannot see, and our minds can barely wander. Out there in the deepest darkness, galaxies spin like distant lighthouses, their ancient light carrying messages from when the cosmos was young and stars were just beginning their eternal dance. We will travel through billions of years and trillions of miles, drifting past everything familiar until we reach that mysterious boundary where the known universe fades into shadow and speculation. Along this gentle journey through the night, you will discover how far we can see, what waits at those impossible distances, and what it means to search for an edge in something that may have no end. Let yourself relax as we float together through the cosmic dark, moving slowly and peacefully toward understanding, toward wonder, toward sleep. The universe is vast and patient, and so shall we be as we explore its furthest reaches, one quiet thought at a time, one distant star at a time, drifting softly through the infinite night. The comfortable beginning. Before we can understand the edge of the universe, we must first feel comfortable with our own small place within it, here on Earth, under familiar skies. When you look up on a clear night far from city lights, you can see perhaps 3,000 stars scattered across the darkness, like diamonds on velvet. Each of those stars is a sun, perhaps with planets of its own, each one sitting at distances so enormous that the fastest spaceship we have ever built would take thousands of years to reach even the closest one. The light from these stars has been traveling toward your eyes for years, sometimes for decades or even centuries, crossing the empty space between their distant locations and your backyard. This means that when you see a star, you are looking backward through time, seeing that star not as it is now, but as it was when its light began the journey toward Earth. Some of the stars you see might have already died, exhausted their fuel, and faded away, but their final light is still traveling toward us across the cosmic distance. This simple truth, that light takes time to travel, becomes the key to understanding everything about the edge of the universe and our ability to see it. Our own sun sits at the center of our small corner of space. A warm yellow star of medium size that has been shining steadily for about 4.5 billion years. Earth orbits this sun at a comfortable distance, not too close and not too far, receiving just enough warmth to allow liquid water and life to flourish. Beyond Earth, the other planets of our solar system circle the sun in their own patient rhythms, from swift Mercury racing around every 88 days to distant Neptune taking 164 years to complete a single orbit. The solar system extends far beyond Neptune into a realm of icy objects and dwarf planets. But even these distant frozen worlds are just the beginning of our journey outward. If you could travel at the speed of light, you would cross the entire solar system from the sun to the edge of its influence in just over a day. But the nearest star beyond our sun waits more than 4 years away at that incredible speed. Space is mostly empty. Vast distances separating tiny islands of matter, and this emptiness only grows larger as we move toward the edge of the universe. The ancient astronomers who studied the night sky thousands of years ago believed that the stars were fixed points painted on a celestial sphere that rotated around Earth, and they thought this sphere marked the edge of all existence, a final boundary beyond which nothing could be. They had no way of knowing that each star was actually a distant sun, or that beyond those visible stars lay billions more, or that the universe extended far beyond anything they could imagine in their most ambitious dreams. Discovering the depth of space. For thousands of years, humans looked at the night sky and wondered about its depth. But we had no way to measure how far away the stars truly were. The stars seemed to be all at the same distance, painted on that imaginary celestial sphere, moving together as the Earth rotated beneath them. It was not until the early 1800s that astronomers developed techniques sensitive enough to measure the distances to nearby stars using a method called parallax. Parallax is the apparent shift in position that an object shows when you view it from different locations. The same effect that makes your thumb appear to jump against a distant background when you look at it with first one eye and then the other. By observing a nearby star at different times of year when Earth is on opposite sides of its orbit around the Sun, astronomers could see a tiny shift in the star's position against the background of more distant stars. The amount of shift told them how far away the star must be. And these first measurements revealed that even the nearest stars were at distances almost incomprehensible to human minds. A star might be 20 trillion miles away, a number so large that it becomes meaningless in everyday terms. So astronomers invented new units of measurement better suited to cosmic distances. The light year, the distance that light travels in 1 year moving at 186,000 miles per second, became the standard unit for measuring stellar distances. The nearest star beyond our Sun, Proxima Centauri, sits about 4 light years away, meaning its light takes 4 years to reach Earth. When you see Proxima Centauri in a telescope, you are seeing it as it was 4 years ago, looking backward through time across the intervening space. As telescopes improved and techniques advanced, astronomers measured distances to more and more stars, building up a 3-dimensional map of our stellar neighborhood and discovering that stars are not evenly distributed, but cluster together in vast groups. Our Sun belongs to a great gathering of stars called the Milky Way galaxy, a spiral-shaped collection of several hundred billion stars bound together by gravity and rotating slowly around a common center. The Milky Way spans about 100,000 light-years from edge to edge, and our Sun sits roughly halfway out from the center in one of the spiral arms. On a dark night far from city lights, you can see the Milky Way as a faint band of light stretching across the sky. The combined glow of millions of distant stars, too faint to see individually, but creating a soft, luminous river flowing through the darkness. For a long time, many astronomers believed that the Milky Way was the entire universe, that it contained all the stars that existed, and that beyond its edges lay only empty darkness extending forever. This comfortable view of a finite universe contained within our galaxy was about to be shattered by new observations that would reveal depths of space beyond anyone's imagination. The island universes appear scattered among the stars of the Milky Way. Astronomers had long noticed fuzzy patches of light that did not look like stars, but appeared as small clouds or nebulae. Some of these nebulae were clearly clouds of gas and dust within our own galaxy, glowing with the light of hot stars embedded within them, or illuminated by the radiation of dying stars. But other nebulae had a different character, appearing as spiral or elliptical shapes with structure and form. And astronomers argued for decades about whether these spiral nebulae were relatively nearby objects within the Milky Way, or whether they might be distant galaxies far beyond our own. The debate continued until the early 1920s, when astronomer Edwin Hubble, using the largest telescope in the world at that time, discovered special stars called Cepheid variables in one of these spiral nebulae. Cepheid variables are stars that brighten and dim in a regular rhythm. And astronomers had discovered that the period of this rhythm is directly related to the star's true brightness. By measuring how bright a Cepheid appears from Earth and comparing that to how bright it truly is, astronomers can calculate its distance using the simple principle that light dims with distance. Hubble's discovery of Cepheids in the Andromeda Nebula allowed him to measure its distance, and the result was stunning. Andromeda lay nearly 1 million light-years away, far beyond any star in the Milky Way, and proving conclusively that it was a separate galaxy, an island universe of billions of stars existing independently in the vastness of space. The universe had suddenly grown enormously larger, and what astronomers had thought was everything turned out to be just one galaxy among countless others. As more powerful telescopes were built and techniques improved, astronomers discovered galaxy after galaxy, each one containing billions or hundreds of billions of stars, each one separated from its neighbors by millions of light-years of mostly empty space. The universe revealed itself as a cosmic ocean filled with island galaxies, each one a vast collection of stars, gas, dust, and mysterious dark matter bound together by gravity. These galaxies are not scattered randomly, but form patterns and structures, clustering together in groups and clusters, connected by filaments and sheets, creating a cosmic web that extends as far as telescopes can see. The Milky Way belongs to a small cluster called the Local Group, containing about 50 galaxies, most of them small dwarf galaxies, but including 3 large spiral galaxies: the Milky Way, Andromeda, and the Triangulum galaxy. The Local Group spans about 10 million light-years across and represents just one tiny corner of the observable universe. Beyond the Local Group lie larger structures, including the Virgo cluster, containing thousands of galaxies, about 50 million light-years away. And beyond that, the enormous Laniakea supercluster, of which our Local Group is just a small outlying member. The discovery of these vast distances and enormous structures raised new questions about the universe. How far does it extend? Is there an edge? And if so, what lies beyond? Does the universe go on forever? Or does it have a boundary? These questions, once the province of philosophers, were becoming questions that astronomers might actually be able to answer through observation and measurement. The universe is expanding. While astronomers were mapping the distances to galaxies and discovering the vast scale of the universe, they were also studying the light from these distant galaxies in detail, breaking it into spectra that revealed information about the galaxy's composition and motion. When light from a moving object is spread into a spectrum showing all its colors, the specific patterns of dark lines created by elements absorbing certain wavelengths shift toward the red end of the spectrum if the object is moving away from us, or toward the blue end if the object is approaching. This Doppler shift, named after the physicist who explained it, is the same effect that makes a train whistle sound higher in pitch as it approaches and lower as it moves away. By measuring the Doppler shift in galaxy spectra, astronomers could determine whether galaxies were moving toward or away from Earth and how fast they were moving. Edwin Hubble, working with his colleague Milton Humason in the late 1920s, measured the spectra of dozens of galaxies and made an astonishing discovery. Nearly all galaxies showed redshifts, meaning they were moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, suggested something profound about the nature of the universe. The universe was not static and unchanging, as everyone had assumed, but was expanding, with galaxies moving apart from each other as space itself stretched and grew larger. This expansion does not mean that galaxies are flying through space away from Earth, as if we were at the center of some cosmic explosion. Instead, space itself is expanding, carrying galaxies along with it like raisins in a rising loaf of bread, where every raisin moves away from every other raisin as the dough expands. An observer on any galaxy would see all other galaxies moving away, and the farther away they looked, the faster those distant galaxies would appear to recede. The discovery of cosmic expansion revolutionized our understanding of the universe and led to the development of the Big Bang theory. The idea that the universe began in an extremely hot and dense state and has been expanding and cooling ever since. If the universe is expanding now, then it must have been smaller in the past. And if we run time backward far enough, we reach a moment about 13.8 billion years ago when the universe was compressed into an infinitesimally small point of infinite density and temperature. This moment, the Big Bang, marks the beginning of space and time itself. The moment when everything that exists came into being and began its expansion outward. The cosmic expansion gives us a new way to think about distance and the edge of the universe. Light from distant galaxies takes time to reach Earth. And the farther away a galaxy is, the longer its light has been traveling, and the farther back in time we see when we observe it. The most distant galaxies we can see are so far away that their light has been traveling for billions of years, showing us those galaxies as they were in the ancient past when the universe was young. Looking back through time, every observation we make of the distant universe is also a look backward through time. And this simple fact becomes increasingly important as we approach the edge of what we can see. When you look at the sun, you see it as it was 8 minutes ago, because that is how long light takes to travel from the sun to Earth. When you look at the nearest star beyond the sun, you see it as it was 4 years ago. When you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago, back when early humans were just beginning to walk upright on the plains of Africa. As we look deeper into space at more distant galaxies, we look further back through time, seeing the universe at progressively earlier stages in its history. Galaxies a billion light years away appear as they were a billion years ago. When their light began its journey toward Earth, galaxies 10 billion light years away show us the universe as it was 10 billion years ago, just a few billion years after the Big Bang, when galaxies were younger and star formation was more vigorous than it is today. This ability to look backward through time makes astronomy unique among sciences. A biologist studying evolution must infer what ancient creatures were like from fossils and genetic evidence. But an astronomer studying the evolution of galaxies can actually see galaxies at different ages simply by looking at different distances. The most distant galaxies reveal the early universe directly, showing us what galaxies looked like when they were first forming and helping us understand how the universe evolved from its simple beginnings to the complex structures we see nearby today. As we push our observations to greater and greater distances, trying to see farther back through time, the galaxies we observe become fainter and redder. their light stretched by the expansion of space during its long journey to Earth. This cosmological redshift is different from the Doppler shift caused by motion through space, though they appear similar. Cosmological redshift occurs because the wavelength of light gets stretched as space itself expands during the light's journey, shifting the light toward redder, longer wavelengths. The amount of redshift tells us how much the universe has expanded since the light was emitted, and therefore how far back in time we are looking. Astronomers use redshift as a measure of distance for very remote objects, talking about galaxies at redshift 2 or redshift 6, where higher numbers mean greater distances and earlier times. A galaxy at redshift 2 appears as it was when the universe was about 3 billion years old, while a galaxy at redshift 6 shows us the universe at less than 1 billion years old in its relative infancy. The most distant galaxies ever observed have redshifts greater than 10, showing us the universe at just a few 100 million years after the Big Bang, a time when the first stars and galaxies were forming from the primordial hydrogen and helium created in the Big Bang itself. These ancient galaxies look very different from nearby galaxies, appearing smaller, more irregular, and actively forming stars at prodigious rates, burning through their gas supplies to create new generations of stars that would live, die, and enrich the universe with heavier elements. The observable universe takes shape. As we continue our gentle journey outward through space and backward through time, we approach a fundamental limit to what we can see, a boundary that defines the edge of the observable universe. This edge is not a physical barrier or a place where the universe ends, but rather a horizon beyond which light has not had time to reach us since the Big Bang. Remember that the universe is about 13.8 billion years old, and light travels at a finite speed of 186,000 miles per second. This means that light has had only 13.8 billion years to travel through space since the beginning of time. You might think that the edge of the observable universe should therefore be 13.8 billion light years away. But the actual distance is much greater because the universe has been expanding while light travels through it. A photon emitted from a distant galaxy shortly after the Big Bang has been traveling toward Earth for nearly the entire age of the universe. But during that time, the space between us and that galaxy has been stretching, expanding, carrying that galaxy farther and farther away, even as its light moves toward us. The galaxy that emitted the light we see today from the edge of the observable universe is now about 46 billion light years away, though its light has been traveling for only 13.8 billion years. This creates a sphere around Earth, centered on our location, that defines the observable universe. Everything within this sphere of about 46 billion light years radius is potentially observable because light from those regions has had time to reach us. Everything beyond this distance is beyond the observable universe, not because it does not exist, but because its light has not yet had time to arrive. The observable universe contains everything we can see, everything we can detect with any instrument, everything we can know about through direct observation. It is like standing in a vast fog where you can see clearly for a certain distance, but beyond that distance, the fog obscures everything. The edge of visibility is not a wall or a boundary of the fog itself, but simply the limit of how far you can see through it. In the case of the universe, the fog is not really fog, but simply the limit imposed by the age of the universe and the speed of light. Beyond the edge of our observable universe, space almost certainly continues, filled with more galaxies, more stars, more planets. But we cannot see them, and never will, unless we wait longer and let their light reach us. As time passes and the universe ages, the observable universe grows larger as light from more distant regions finally completes its journey to Earth. In principle, if we wait long enough, we will be able to see farther and farther. But in practice, the accelerating expansion of the universe complicates this picture, as we will discover later in our journey. The observable universe contains everything we have discussed so far. All the stars and galaxies and clusters and superclusters, all arranged in the cosmic web of structure that formed from tiny density fluctuations in the early universe. Current estimates suggest that the observable universe contains about 2 trillion galaxies, though some estimates run even higher. And each galaxy contains millions or billions or hundreds of billions of stars. The total number of stars in the observable universe may exceed 10 to the 24th power, a number so large that it exceeds the number of grains of sand on all the beaches on Earth. The cosmic microwave background. As we look deeper into space and farther back in time, approaching the edge of the observable universe, we eventually reach a moment in cosmic history when the universe was so young that galaxies had not yet formed and stars had not yet ignited. At these ancient times, looking back more than 13 billion years, the universe was filled with hot, dense gas, primarily hydrogen and helium created in the Big Bang, beginning to collapse into the first structures under the influence of gravity. But even earlier than this, before the first stars formed, the universe was too hot for atoms to exist at all. In its first few 100,000 years, the universe was so hot that electrons and atomic nuclei could not combine to form neutral atoms, but instead existed as a plasma, a sea of electrically charged particles. This plasma was opaque to light because photons could not travel far before being scattered by the free electrons, absorbed and re-emitted in random directions, unable to move freely through space. The universe at this time was like being inside a glowing cloud, bright and hot everywhere, with no distant views possible because light could not travel in straight lines. Then, about 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and nuclei could finally combine to form neutral atoms, an event called recombination. With the free electrons locked up in atoms, light could suddenly travel freely through space without being constantly scattered. And the universe became transparent for the first time, and the light that was traveling through the universe at the moment of recombination has been traveling freely ever since, spreading out in all directions as space expanded and cooled. Today we can detect this ancient light coming to us from all directions in space, not from any particular galaxy or star, but from the universe itself. From that moment when space first became transparent. This is the cosmic microwave background radiation, the CMB, the oldest light in the universe and the most distant thing we can possibly see. The cosmic microwave background marks the edge of our observable universe in terms of electromagnetic radiation, a wall beyond which we cannot see because the universe was opaque before recombination. When we observe the CMB, we are seeing the universe as it was 380,000 years after the Big Bang. Looking back through nearly the entire history of the cosmos, the light from the CMB was originally visible, an infrared light emitted by the hot plasma. But during its 13.8 billion year journey to Earth, that light has been stretched by cosmic expansion into microwave wavelengths. Light with wavelengths of about 1 millimeter that our eyes cannot see, but that can be detected with radio antennas and microwave receivers. The cosmic microwave background appears as a faint glow coming uniformly from all directions, with a temperature of about 2.7 degrees above absolute zero. Incredibly cold but warmer than the empty vacuum of space in the absence of the CMB. This uniform glow fills all of space, bathing the Earth and everything in the universe in these ancient photons that have been traveling since the beginning of time. Ripples in the ancient light. The cosmic microwave background would be perfectly uniform, looking exactly the same in all directions, if the early universe had been perfectly smooth and featureless. But observations reveal that the CMB contains tiny variations in temperature, hot spots and cold spots that differ by only a few parts in 100,000. Barely detectable, but incredibly important. These temperature fluctuations in the CMB are the fingerprints of the early universe, showing us the tiny density variations that existed in the primordial plasma just after the Big Bang. Regions that were slightly denser than average appear as warm spots in the CMB because their higher density meant higher temperature and pressure, while slightly less dense regions appear as cold spots. These density variations may seem insignificant, differing by only one part in 100,000. But they were the seeds from which all cosmic structure grew. The denser regions had slightly stronger gravity and began attracting more matter, growing denser still, while the less dense regions lost matter to their surroundings and became emptier. Over hundreds of millions of years, this process of gravitational collapse amplified the tiny initial density differences into the dramatic structures we see today, the clusters and superclusters of galaxies separated by vast, empty voids, the cosmic web of matter stretching across the universe. By studying the pattern of temperature fluctuations in the cosmic microwave background, astronomers can learn about conditions in the very early universe, measuring its age, its composition, its geometry, and its fate with remarkable precision. The CMB has been mapped in exquisite detail by several generations of satellites and telescopes, each one producing increasingly sharp images of the temperature variations across the sky. These maps show a complex pattern of hot and cold spots of various sizes, ranging from large patches spanning many degrees of sky to tiny features just a fraction of a degree across. The sizes and amplitudes of these features encode information about the physics of the early universe, revealing the amounts of normal matter, dark matter, and dark energy, and confirming the predictions of Big Bang cosmology with stunning accuracy. The cosmic microwave background represents not just the edge of our observable universe, but also the limit of how far back in time we can see using light. Before the CMB, in the first 380,000 years after the Big Bang, the universe was opaque, and we cannot see that era using electromagnetic radiation. This early period is hidden from us behind the CMB, which acts like a wall or screen, showing us only its surface at the moment of recombination, but revealing nothing of what came before. To study the universe earlier than the CMB, astronomers must rely on other signals, such as gravitational waves or cosmic neutrinos that might have escaped from the very early universe, or on theoretical models that extrapolate backward from what we observe. The Dark Ages and First Light. Beyond the cosmic microwave background, hidden from our direct view, lies a period in cosmic history called the Dark Ages. The time between when the universe became transparent at recombination and when the first stars began to shine. During the Dark Ages, the universe was truly dark because no stars existed yet to produce light, and the cosmic microwave background radiation had redshifted to infrared wavelengths that would have been invisible to human eyes. The universe during this period was filled with neutral hydrogen gas, slowly collapsing under gravity into the first structures, gathering in clouds that would eventually become dense enough to ignite nuclear fusion and create the first stars. The Dark Ages lasted for about 100 to 200 million years, a considerable time, but still just a small fraction of the universe's total age. During this period, the universe was cooling as it expanded, and the temperature dropped from about 3,000 degrees Kelvin at recombination to perhaps 30 degrees above absolute zero by the end of the Dark Ages. The cold hydrogen gas was collapsing into dark matter halos, regions where invisible dark matter had concentrated under gravity, creating gravitational wells into which normal matter fell. The first stars to form, called population 3 stars, were probably much more massive than typical stars today, perhaps 100 or more times the mass of the Sun, because the primordial hydrogen and helium from which they formed contained no heavier elements to help cool the gas and allow smaller stars to form. These massive first stars would have burned incredibly hot and bright, living for only a few million years before exploding as supernovae and scattering the first heavy elements, the first carbon and oxygen and iron, into space. The era of the first stars, sometimes called the cosmic dawn, marks the end of the Dark Ages as light began to fill the universe again, for the first time since recombination. These first stars and the first small galaxies they formed began to emit ultraviolet radiation that started to ionize the neutral hydrogen gas filling space, breaking apart atoms and creating bubbles of ionized gas around each star and galaxy. As more stars formed and more galaxies appeared, these bubbles of ionization grew and merged until eventually all the hydrogen in the universe was ionized again. A period called the epoch of rionization that was complete by about 1 billion years after the Big Bang. The light from these first stars and galaxies has been traveling through space for more than 13 billion years, stretched by cosmic expansion into the infrared, and represents some of the most distant objects we can hope to observe with our most powerful telescopes. Finding these first stars and galaxies and studying how they formed and how they reionized the universe has been one of the major goals of astronomy for the past several decades. Searching for the first galaxies, astronomers have been pushing the limits of observational technology for years in an effort to find and study the most distant galaxies, those faint pinpricks of light from the early universe that show us the cosmic dawn and the epoch of rionization. These ancient galaxies are extraordinarily difficult to observe because they are extremely faint, and their light has been redshifted from visible wavelengths into the infrared, requiring specialized instruments that can detect infrared light while blocking the overwhelming infrared glow from Earth's atmosphere and from the telescope itself. The Hubble Space Telescope, orbiting high above the atmosphere, has captured some of the deepest images of the universe ever made. Staring at tiny patches of apparently empty sky for days or weeks to collect enough light to reveal the faintest and most distant galaxies. These deep surveys, including the famous Hubble Deep Field and its successors, show thousands of galaxies in every direction, with the most distant appearing as tiny red smudges, their light stretched by cosmic expansion until only the infrared wavelengths reach us. Some of these galaxies have been studied in detail using spectroscopy to measure their precise redshifts, confirming that we are seeing them as they were less than 1 billion years after the Big Bang, in the very early universe. These ancient galaxies look different from nearby galaxies, appearing smaller, more irregular, and often showing intense star formation, creating stars at rates many times higher than in typical galaxies today. The early universe was a more violent and active place, where gas was plentiful and galaxies were constantly colliding and merging. building up larger structures from smaller building blocks. By observing galaxies at many different distances, and therefore at many different times in cosmic history, astronomers have been able to piece together the story of how galaxies evolve, how they grow larger through mergers, how their star formation rates change over time, and how the universe gradually evolved from a simple place filled with small, irregular galaxies to the complex cosmos we see around us today. With its giant elliptical galaxies, grand spiral galaxies, and rich clusters, the search for ever more distant galaxies continues as new instruments are developed. The James Webb Space Telescope, launched in late 2021, is specifically designed to study the infrared light from the first stars and galaxies. With a much larger mirror than Hubble and instruments optimized for infrared wavelengths. Early observations from Webb have already revealed candidate galaxies at redshifts greater than 12, showing us the universe at less than 400 million years after the Big Bang, and potentially pushing back our view nearly to the end of the Dark Ages. These observations test and refine our models of galaxy formation and help us understand how structure emerged from the nearly featureless early universe revealed by the cosmic microwave background. Dark matter shapes the universe. As we drift through our understanding of the distant universe, we must acknowledge that most of what exists out there in the darkness is invisible, undetectable, except through its gravitational influence on the matter and light we can see. This is dark matter, mysterious substance that makes up about 85% of all matter in the universe, but does not emit, absorb, or reflect light or any other electromagnetic radiation. We know dark matter exists because galaxies and galaxy clusters behave as if they contain much more mass than we can see in stars and gas. Galaxies rotate too fast, their outer regions moving so quickly that they should fly apart unless held together by gravity from additional unseen mass. Galaxy clusters hold together vast collections of galaxies moving at high speeds, requiring enormous amounts of gravity from dark matter to prevent the cluster from dispersing. The gravitational lensing of light from distant galaxies by foreground clusters reveals the distribution of mass in those clusters, showing that the mass extends far beyond the visible galaxies and exists in amounts far greater than the visible matter can account for. All evidence points to the existence of some form of matter that participates in gravity and helps shape the structure of the universe, but remains invisible to all our telescopes and detectors. The nature of dark matter remains one of the greatest mysteries in physics, with many theoretical candidates proposed, but none confirmed. Dark matter might consist of exotic particles that interact only through gravity and the weak nuclear force. Particles that would pass through normal matter almost without interaction, making them incredibly difficult to detect directly. Laboratory experiments deep underground, shielded from cosmic rays and other interference, have been searching for dark matter particles for decades, looking for the rare occasions when a dark matter particle might collide with an atomic nucleus and produce a tiny detectable signal. But so far, these searches have found nothing definitive. Despite our inability to see or directly detect dark matter, we can map its distribution throughout the universe by observing its gravitational effects on visible matter and on light. Dark matter is not evenly spread through space, but concentrates in halos around galaxies and in larger structures threading through the cosmos. Computer simulations of cosmic evolution that include dark matter show the universe developing structure in a way that closely matches observations, with dark matter forming a cosmic web of filaments and nodes, and normal matter falling into the gravitational wells created by dark matter to form galaxies and stars. Without dark matter, the universe would look completely different. And galaxies, as we know them, could not exist because there would not be enough gravity to pull together the large amounts of gas needed to form the hundreds of billions of stars we see. Dark matter was crucial in the early universe for amplifying the tiny density fluctuations in the cosmic microwave background into the large-scale structures we see today. Because dark matter could collapse under gravity even before recombination, when normal matter was still locked in a plasma and prevented from collapsing by radiation pressure. Dark energy and cosmic acceleration. If dark matter is a mystery, then dark energy is an even deeper puzzle. A mysterious force or property of space itself that appears to be pushing the universe apart and causing cosmic expansion to accelerate. For most of the 20th century, after Hubble discovered that the universe is expanding, astronomers assumed that this expansion must be gradually slowing down, decelerated by the gravitational attraction of all the matter in the universe, pulling back against the expansion. The question was not whether the expansion was slowing, but whether it was slowing fast enough that it would eventually stop and reverse, causing the universe to collapse back in on itself in a big crunch, or whether the expansion would continue forever, gradually slowing, but never quite stopping. This question could be answered by measuring the expansion rate of the universe at different times in cosmic history, comparing the current expansion rate to the expansion rate in the distant past by observing very distant galaxies and measuring how fast they are receding. In the late 1990s, two independent teams of astronomers undertook precisely this project, using special exploding stars called Type Ia supernovae as distance markers. These supernovae are extremely bright and have very consistent peak luminosities, making them excellent standard candles for measuring distances to faraway galaxies. By observing many Type Ia supernovae in distant galaxies and measuring both their distances and their redshifts, the teams expected to determine how much the cosmic expansion had slowed over time. The results shocked everyone. Instead of finding that the expansion had slowed as expected, the observations showed that the expansion is actually speeding up, accelerating, getting faster as time goes on. This was completely unexpected and contradicted all theoretical predictions, requiring some new component in the universe. Some form of energy that creates a repulsive gravitational effect pushing space apart. This mysterious component was named dark energy, and subsequent observations have confirmed its existence and measured its properties with increasing precision. Dark energy makes up about 68% of the total energy content of the universe, dominating over both dark matter at 27% and normal matter at just 5%. The nature of dark energy is unknown, and several possibilities have been proposed. It might be a property of space itself, a vacuum energy or cosmological constant that creates a constant pressure pushing space apart. Einstein's equations of general relativity allow for such a cosmological constant, and Einstein actually introduced it into his equations before Hubble discovered cosmic expansion, trying to create a static universe that would neither expand nor contract. After expansion was discovered, Einstein abandoned the cosmological constant, allegedly calling it his greatest blunder, but it has now returned as a possible explanation for dark energy. Alternatively, dark energy might be a dynamic field that changes over time, similar to fields associated with fundamental particles, but operating on cosmic scales and with exotic properties that create repulsive gravity. Whatever its nature, dark energy has profound implications for the fate of the universe and for the ultimate edge of the observable universe. The future of cosmic expansion. The discovery of dark energy and accelerating expansion changes our understanding of how the universe will evolve in the future and affects what we can ultimately see from our vantage point in space. in a universe that expands at a constant rate or that decelerates over time. We can eventually see light from increasingly distant regions as that light has more time to reach us. The observable universe would continue to grow larger as time passes, eventually encompassing more and more of the total universe. But in an accelerating universe dominated by dark energy, the situation is different and more limited. As cosmic expansion accelerates, distant regions of space recede from us faster and faster, and there comes a distance beyond which the recession velocity exceeds the speed of light. This does not violate relativity because the recession is caused by expanding space rather than motion through space. But it does mean that light from beyond a certain distance cannot reach us because it is swimming against a current of expanding space that is carrying it away faster than it can approach. This creates what is called the cosmic event horizon, a boundary beyond which events cannot affect us and from which no signal can ever reach us. Galaxies beyond this event horizon are receding from us faster than light and will never be observable no matter how long we wait. And in fact, they are becoming increasingly distant as time goes on, their light never making any progress toward us. The cosmic event horizon lies at a distance of about 16 billion light-years from Earth in terms of the distance to those galaxies right now, though those galaxies emitted the light we could potentially see from them when they were much closer. Any galaxy currently beyond the cosmic event horizon is forever beyond our ability to observe. And as time goes on, more and more galaxies will cross this horizon and disappear from our view as accelerating expansion carries them away. This creates a future universe that becomes increasingly lonely and empty from the perspective of an observer in the Milky Way or any other galaxy. Billions of years from now, if dark energy continues to dominate as current observations suggest, the galaxies we see today in our cosmic neighborhood will have drifted farther away, and more distant galaxies will have disappeared beyond the cosmic event horizon. Eventually, in hundreds of billions of years, all galaxies beyond our local group will have disappeared from view, carried away by cosmic expansion beyond the point where their light can reach us. An astronomer in that distant future, looking out from Earth or whatever remains of it, would see only the merged remnants of the Milky Way and Andromeda and the small dwarf galaxies of our local group, surrounded by absolute darkness with no other galaxies visible anywhere in the sky. Without knowledge of the historical observations we have made, such a future astronomer might conclude that their merged galaxy was the entire universe, alone in an infinite empty cosmos, unable to discover the truth about cosmic expansion or the Big Bang, or the billions of other galaxies that exist but have disappeared beyond the event horizon. The shape and size of the universe. Throughout our journey toward the edge of the universe, we have been discussing the observable universe, the region within about 46 billion light-years, from which light has had time to reach us since the Big Bang. But what about the universe beyond what we can observe? Does the universe continue forever in all directions, extending infinitely? Or does it have a finite size with some kind of boundary or edge? These questions touch on the shape or geometry of the universe, a property determined by its total energy density and curvature. Einstein's general relativity describes how mass and energy curve space-time, and on cosmic scales, the average density of matter and energy determines whether space itself is curved globally in ways that affect the overall geometry and topology of the universe. There are three basic possibilities for the geometry of the universe, each with different implications for its size and whether it has an edge. If the total energy density of the universe equals a critical value called the critical density, then space is flat on large scales. meaning that parallel lines remain parallel forever, and the angles of a triangle add up to exactly 180 degrees. A flat universe extends infinitely in all directions, with no edge or boundary, continuing forever beyond the observable universe, with more galaxies and more space without end. If the total energy density exceeds the critical density, then space has positive curvature, bending back on itself like the surface of a sphere where parallel lines eventually converge and triangles have angles that add up to more than 180 degrees. A positively curved universe is finite in size but has no edge, just as the surface of a sphere is finite but has no boundary where it ends. In such a universe, if you could travel far enough in one direction, you would eventually return to your starting point from the opposite direction, having circumnavigated the universe. If the total energy density is less than the critical density, space has negative curvature like a saddle shape, where parallel lines diverge and triangles have angles adding up to less than 180 degrees. A negatively curved universe extends infinitely like a flat universe, with no edge or boundary, continuing forever in all directions. Observations of the cosmic microwave background have measured the geometry of the universe with remarkable precision by examining the sizes of the temperature fluctuations, which are affected by the curvature of space. These measurements indicate that the universe is very close to flat, with curvature consistent with zero within observational uncertainties. A flat universe is actually a special case requiring the energy density to equal the critical density exactly. And the fact that observations find flatness suggests that either the universe is exactly flat by some underlying principle, or it is so close to flat that any slight curvature is undetectable with current instruments. Infinite universe or finite? If the universe is flat or negatively curved, as observations suggest, then it extends infinitely in all directions. And there is no edge to the universe itself, only the edge of the observable universe beyond which we cannot see. An infinite universe is difficult for the mind to grasp because it means there is no center and no boundary. And it means the universe contains an infinite amount of matter and energy spread across infinite space. In an infinite universe, every possible arrangement of atoms and particles occurs somewhere, repeated infinitely many times across infinite space, leading to strange philosophical implications. If the universe is infinite and filled with matter distributed similarly to what we observe in our observable universe, then there must be other regions far beyond our observable universe that look exactly like our region, with identical galaxies and even identical copies of Earth, with identical people living identical lives. This follows from simple probability, because with an infinite number of regions, every possible configuration must occur, and must occur infinitely many times. These ideas push at the boundaries of science and philosophy, entering realms that are difficult or impossible to test observationally. The possibility of an infinite universe raises questions about what we mean by the universe and whether regions beyond our observable universe should even be considered part of the same universe, if we can never observe them or affect them. Some cosmologists define the universe as equivalent to the observable universe, arguing that anything we can never observe or interact with is not meaningfully part of our universe, while others consider the entire infinite expanse as one universe, with our observable portion being just an infinitesimally small patch of the whole. These questions become even more complex when we consider inflationary cosmology, a theory developed in the early 1980s to explain certain properties of the universe that are otherwise difficult to understand. Inflation proposes that the universe underwent a brief period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, growing from subatomic size to perhaps the size of a grapefruit, or larger in less than a trillionth of a second. This rapid expansion smoothed out any initial irregularities and stretched any initial curvature to near flatness, explaining why the universe appears so uniform and flat today. Inflation also predicts that quantum fluctuations in the inflating space created the tiny density variations that we see imprinted in the cosmic microwave background, and that later grew into galaxies and large-scale structure. Observations of the CMB have confirmed several predictions of inflation, lending support to the theory, though inflation itself remains difficult to test directly and many details remain uncertain. One implication of inflation is that our observable universe is just one patch of a much larger inflated region. And different patches may have inflated by different amounts or at different times, creating a possibility of multiple separate regions with different properties. An idea called eternal inflation or the inflationary multiverse. Beyond the observable horizon, as we float quietly through these ideas, drifting towards sleep while contemplating the edge of the universe, we should acknowledge that there may be no single edge, but instead multiple horizons and boundaries of different types. We have discussed the cosmic event horizon, beyond which distant galaxies are receding faster than light and can never be observed. And we have discussed the surface of last scattering, where the cosmic microwave background originates, marking the limit of how far back in time we can see using light. But there may be other boundaries and edges in different contexts, including the particle horizon, which defines the maximum distance that any signal could have traveled since the Big Bang, and beyond which no causal connection is possible between events. There is also the question of what lies beyond our observable universe, in the sense of what the universe looks like at regions far beyond our ability to see. If the universe is infinite and roughly uniform on large scales, as observations suggest, then the distant universe beyond our observable horizon probably looks much like our observable universe, filled with galaxies and clusters and voids, with structures forming through gravity and stars living and dying in endless cycles. In this view, there is nothing particularly special about the edge of our observable universe, except that it marks the limit of our perception, not any fundamental change in the nature of space or matter. However, inflationary cosmology and some theories of fundamental physics suggest the possibility that very far beyond our observable universe, conditions might be different from what we see locally. In the inflationary multiverse scenario, different regions of space that inflated separately might have different physical properties, different values for fundamental constants like the strength of gravity or the mass of the electron, different numbers of dimensions of space, or different physical laws entirely. In such a scenario, our observable universe is a bubble within a vast, possibly infinite inflating space, and other bubbles with different properties exist far beyond our horizon, forever beyond our ability to observe or interact with them. These ideas venture into realms of speculation and theory that are difficult or impossible to test, raising questions about whether such untestable ideas can be considered science or whether they are more akin to philosophy. Some physicists embrace these speculative theories as natural extensions of well-tested physics into new domains, while others argue that science should restrict itself to testable predictions and that speculation about unobservable universes or multiverses is not productive. Regardless of these debates, the ideas remind us of the profound mystery that remains at the edge of our understanding, where the known universe fades into the unknown and questions multiply faster than answers. the distant future of the universe. Looking forward in time rather than back, we can use our understanding of cosmic expansion and dark energy to predict how the universe will evolve in the distant future. And this future evolution affects what we mean by the edge of the universe in a practical sense. As we have discussed, the accelerating expansion driven by dark energy will cause more and more galaxies to disappear beyond our cosmic event horizon, creating an increasingly empty universe from the perspective of future observers in our galaxy. But the effects go deeper than just losing sight of distant galaxies. Accelerating expansion means that space itself is being stretched at an ever-increasing rate. And if dark energy continues to dominate with constant strength, the expansion rate will grow exponentially, eventually becoming so rapid that even structures currently bound by gravity will be torn apart. In the very distant future, trillions of years from now, galaxies will have exhausted their supplies of gas and will no longer be forming new stars. Existing stars will gradually burn out and die, some fading as white dwarfs, others exploding as supernova and leaving behind neutron stars or black holes. The universe will grow darker and colder as the last stars wink out and matter becomes increasingly dispersed across ever-expanding space. Within individual galaxies, star systems will occasionally collide or be ejected into intergalactic space by gravitational interactions. And over extraordinarily long timescales, galaxies themselves may evaporate as their stars escape or fall into the central supermassive black hole. These processes operate on timescales of trillions or quadrillions of years, so long that they are difficult for human minds to grasp. But in a universe that may exist forever, even these vast timescales eventually pass. In an even more distant future, if dark energy continues to accelerate expansion indefinitely, space may eventually be stretching so rapidly that even bound structures like individual galaxies or solar systems are torn apart in an event sometimes called the Big Rip. Whether this occurs depends on the precise nature of dark energy and whether its strength increases over time, remains constant, or decreases. Current observations are consistent with a cosmological constant that remains constant over time, in which case bound structures held together by gravity will remain intact indefinitely, even as the space between separate structures expands. But if dark energy grows stronger over time, as some theoretical models suggest is possible, then eventually everything would be torn apart. First galaxy clusters, then galaxies, then solar systems, then planets, and finally atoms themselves as space expands so rapidly that even the electromagnetic forces holding atoms together cannot resist the pull of expanding space. This Big Rip scenario is speculative and depends on assumptions about dark energy that we cannot currently test. But it represents one possible ultimate fate for the universe and one possible ultimate edge. A moment in time beyond which no structures can exist because expanding space has torn everything apart down to the subatomic level. Time itself and the beginning. As we drift closer to sleep, let us consider time itself and the question of whether time has an edge, a beginning or an end that marks the boundary of the temporal universe, just as the observable universe marks a boundary in space. We have discussed the Big Bang as the beginning of the universe, the moment about 13.8 billion years ago when space and time came into existence and began expanding from an extremely hot and dense state. But what does it mean to say that time began at the Big Bang? What existed before the Big Bang? And does that question even make sense? According to general relativity and standard Big Bang cosmology, time itself began at the Big Bang, and there is no before because time did not exist before that moment. Asking what came before the Big Bang is like asking what lies north of the North Pole. The question is meaningless because the concept of before requires time, and time does not extend beyond the beginning of time. This idea is philosophically challenging because our everyday experience and intuition suggest that every event has a cause that came before it, and that time flows continuously from past to future without beginning or end. The idea that time itself could have a beginning seems to violate our sense of how things work. And yet the mathematics of general relativity, when applied to an expanding universe, points toward a singularity, a moment when the universe was compressed to infinite density and infinite curvature, and where the laws of physics as we know them break down. At the singularity, time and space lose their usual meanings, and we cannot use our current theories to describe what happens there or whether anything exists beyond it. The singularity represents an edge to our knowledge and our ability to understand the universe using general relativity, and it suggests that a more complete theory, combining general relativity with quantum mechanics, may be needed to describe the very beginning of the universe. Quantum theories of gravity, such as string theory or loop quantum gravity, attempt to describe what happens at the Planck scale, the incredibly tiny scale of about 10 to the minus 35 meters and 10 to the minus 43 seconds, where quantum effects of gravity become important. At this scale, space and time may not be continuous and smooth, but might have a discrete, grainy structure. And the singularity of classical general relativity might be replaced by something less extreme. Perhaps a bounce where the universe contracted from a previous phase and then expanded again. Or perhaps a quantum tunneling event where the universe emerged from nothing through a quantum process similar to how particles can appear spontaneously from the vacuum in quantum field theory. Quantum origin and eternal questions. These quantum theories of the universe's origin are highly speculative and currently beyond our ability to test observationally, but they represent the frontier of theoretical physics' attempt to understand the ultimate beginning, the edge of time itself. In some scenarios, the universe has no true beginning, but exists eternally in some form, perhaps cycling through repeated expansions and contractions, or perhaps existing as one bubble in an eternally inflating multiverse where new universes are constantly being created through quantum processes. In other scenarios, the universe truly began from nothing, emerging through quantum tunneling from a state with no space, no time, and no matter. A spontaneous creation event that requires no cause because causation itself requires time which did not exist before creation. These ideas challenge our intuitions and our concepts of existence, reality, and causation, pushing at the boundaries not just of physics, but of philosophy and metaphysics. The question of why there is something rather than nothing, why the universe exists at all, may ultimately be unanswerable by science, because science deals with how things work rather than why they exist. Or perhaps the question dissolves under careful analysis, as some philosophers have suggested, arguing that the existence of the universe is simply a brute fact that requires no explanation, or that in quantum mechanics, the concept of nothing is unstable, and something must inevitably appear. As we contemplate these deep questions at the edge of time and existence, we should remember that science has limits, and that beyond those limits lie questions that blend into philosophy and theology. Questions about meaning and purpose and ultimate reality that cannot be answered by observation and experiment alone. The edge of the universe, both in space and in time, marks not just a physical boundary, but an epistemological boundary, the limit of what we can know through empirical investigation. beyond that boundary, speculation and imagination take over. Guided by the hope that someday, new observations or new theories will push that boundary a little farther and reveal new truths about the cosmos. But there may always be an edge to our knowledge, an ultimate horizon beyond which we cannot see. And learning to be comfortable with that uncertainty and that mystery is part of being human in a vast and ancient universe that we are only beginning to understand. The universe keeps its deepest secrets, and perhaps that is as it should be, leaving room for wonder and humility and the recognition that we are small and brief in the cosmic scheme. Temporary patterns of matter and energy, briefly aware of themselves before dissolving back into the darkness from which we came. The multiverse speculation. At the very frontier of cosmological theory, some physicists have proposed that our universe is not alone, but is one of many universes existing in parallel, together forming a multiverse of staggering scope and variety. These multiverse theories come in several flavors, each proposing different types of parallel universes with different properties and different relationships to our own. The quantum multiverse, or many worlds interpretation of quantum mechanics, suggests that every time a quantum measurement or decision point occurs, the universe branches into multiple versions, each one representing a different outcome. In this view, there are countless parallel universes where every possible history has occurred. Universes where you made different choices, where historical events unfolded differently, where different versions of reality play out in endless variation. The quantum multiverse is not a multiverse in the sense of separate regions of space, but rather a multiverse of branching timelines or parallel realities, all existing simultaneously in some higher dimensional space of possibilities. The inflationary multiverse we discussed earlier proposes that our observable universe is one bubble in an eternally inflating space where new bubbles are constantly forming, each one potentially with different physical laws and constants determined by how fields settled into their vacuum states during inflation. These bubble universes are separated by regions of inflating space and can never interact or communicate with each other, making them permanently beyond our ability to observe. The landscape multiverse arising from string theory suggests that there may be an enormous number of possible vacuum states or ground states of the universe, perhaps 10 to the 500th power or more, each one corresponding to a different possible universe with different particles, forces, and laws of physics. If different regions of the multiverse settle into different vacuum states, then there would be many different pocket universes with wildly different properties. And the laws of physics we observe in our universe would be just one possibility among countless others. These multiverse theories are controversial within the physics community because they predict the existence of things that are in principle unobservable, raising the question of whether such predictions are scientific or whether science should restrict itself to testable predictions about the observable universe. Proponents argue that multiverse theories arise naturally from well-tested physics like quantum mechanics and inflation, and that if a theory successfully explains observable phenomena and makes testable predictions, we should take seriously all of its predictions, even if some of them involve unobservable regions or universes. Critics argue that without observational tests, multiverse theories are speculation rather than science, and that invoking unobservable universes to explain features of our universe is not satisfying and does not increase our understanding. Anthropic reasoning and fine-tuning. One argument that has been made in favor of multiverse theories involves the apparent fine-tuning of the physical constants and laws of our universe for the existence of life. Many features of our universe seem to be precisely tuned to values that allow complex chemistry, stable stars, and ultimately life to exist. If the strength of gravity were slightly different, stars might burn too fast or too slow to allow life to evolve. If the nuclear forces were slightly different, the elements necessary for life might not form in stars. If the cosmological constant or dark energy were much larger than observed, the universe would have expanded so rapidly that galaxies and stars never formed. These apparent coincidences have puzzled physicists and have led some to argue that the universe shows evidence of design or that its properties require explanation beyond mere chance. The multiverse provides a possible explanation for fine-tuning through anthropic reasoning. If there are many universes with different physical constants and laws, then most of them would not be capable of supporting life. But a few would have conditions that allow complexity and life to emerge. We necessarily find ourselves in one of the rare life-supporting universes because we could not exist in the others. And so the apparent fine-tuning is explained not by design, but by selection bias. We observe a fine-tuned universe because only fine-tuned universes contain observers to notice the fine-tuning. This anthropic argument is clever but controversial, with critics pointing out that it is not predictive and does not help us understand why specific constants have the values they do. It also raises philosophical questions about the nature of explanation and whether anthropic reasoning is satisfying or merely replaces one mystery with another. The debate continues, with some physicists embracing anthropic reasoning and multiverse theories, while others seek alternative explanations for fine-tuning, or argue that the apparent fine-tuning is not as impressive as it seems, and that life might be possible in a wider range of conditions than we currently imagine. Regardless of which view is correct, these discussions highlight how the question of the edge of the universe leads naturally into deep questions about existence, probability, and the nature of physical law. At the very edge of the universe, at the boundary between the known and the unknown, we encounter not just limits to our observations, but limits to our concepts and our ability to formulate answerable questions. Some questions may have answers that are forever beyond our reach, hidden behind horizons we can never cross or existing in realms we can never observe. And learning to live with that uncertainty requires a certain philosophical maturity and comfort with mystery. The limits of knowledge. Throughout this gentle journey toward the edge of the universe and toward sleep, we have encountered many different types of boundaries and horizons, each one marking a limit to what we can observe or understand. The edge of the observable universe marks the limit of how far we can see given the finite age of the universe and the finite speed of light. The cosmic event horizon marks the boundary beyond which galaxies are receding so fast that we can never observe them. The surface of last scattering, where the cosmic microwave background originates, marks the limit of how far back in time we can see using electromagnetic radiation. The Planck scale marks the limit of where our current theories of physics break down and quantum gravity becomes necessary. Beyond each of these horizons lies the unknown, regions or phenomena that we cannot observe with current technology, or perhaps cannot observe in principle, given the laws of physics. The existence of these horizons and limits raises profound questions about the nature of knowledge and the goals of science. Can we ever understand the universe completely, or will there always be aspects of reality that remain forever hidden from us? Is the universe fundamentally knowable, or does it contain irreducible mysteries that cannot be solved by observation and reason? These are questions that science alone cannot answer, because they are questions about science itself, about the scope and limits of the scientific method. Throughout history, science has repeatedly pushed past apparent limits and explained phenomena that once seemed mysterious or supernatural. What once appeared to be the edge of the world turned out to be simply the edge of exploration. And what once appeared to be the edge of the universe turned out to be just the edge of the Milky Way, with vast regions beyond. Each time we push the boundary of knowledge farther, we discover new phenomena and new questions. And the process continues with no end in sight. This suggests that while there may be practical limits to what we can observe and measure, there may be no fundamental limit to the questions we can ask or the understanding we can achieve. Yet the horizons of the observable universe seem to represent true fundamental limits imposed not by technological limitations, but by the structure of space-time itself. We cannot observe regions beyond the cosmic event horizon because they are receding faster than light, and no future technology can overcome that limitation because it is a consequence of the expansion of space itself. We cannot observe before the cosmic microwave background because the universe was opaque at earlier times, and no form of electromagnetic radiation can bring us information from that era. These appear to be absolute limits on observation, horizons that will never be crossed by any improvement in telescopes or detectors. Unobservable realms and scientific faith, accepting that some things may be forever unobservable, requires a kind of intellectual humility and a recognition that our understanding of the universe is necessarily incomplete and always will be. This is not a failure of science, but rather a consequence of our position as finite beings in a vast and perhaps infinite cosmos, able to observe only a limited portion of what exists. In some ways, believing in regions of the universe beyond our observable horizon requires a kind of faith, or at least an acceptance of theoretical reasoning that goes beyond direct observation. We cannot see these regions, and we never will. But we infer their existence from theories that successfully explain what we can observe. This is not faith in the religious sense, because our beliefs are grounded in evidence and in theories that make testable predictions about the observable universe. But it does require trusting that the laws of physics that work here also work beyond the observable horizon, and that reasoning based on extrapolation from what we observe is valid even when applied to unobservable regions. This is generally considered a reasonable assumption, because physical laws have proven to be universal wherever we have been able to test them, working the same way on Earth as in distant galaxies billions of light years away, and showing no variation with location or time except in ways consistent with general relativity. The uniformity of physical laws throughout the observable universe gives us confidence that they also apply beyond our observable horizon. But it is worth acknowledging that this is an assumption that cannot be directly verified. In the case of multiverse theories, the leap of faith is even larger because we are extrapolating from observed physics to predict the existence of entirely separate universes that we can never observe and that may have different physical laws. Whether such extrapolation is justified or whether it goes beyond the proper bounds of science is a matter of debate. And scientists of good faith can disagree about where to draw the line between legitimate theoretical speculation and unfounded fantasy. What is clear is that as we approach the edge of the universe and the edge of the knowable, we enter a realm where observation and theory become increasingly divorced, where theories make predictions that cannot be tested, and where different interpretations of the same data are possible. This is the frontier of science, the growing edge where new ideas are proposed and debated, where conventional wisdom is challenged, and where the boundaries of human knowledge are pushed outward into the unknown. It is an exciting and sometimes frustrating place to be, because the answers are not yet clear and may not become clear for decades or centuries. But it is also where progress happens and where our understanding of the universe deepens and expands. The poetic edge of existence. As we drift toward the end of our journey and toward peaceful sleep, it is worth reflecting on the deeper meaning of the edge of the universe and what it tells us about our place in the cosmos. The universe is vast beyond comprehension, ancient beyond imagination, filled with wonders and mysteries that we are only beginning to understand. We are small and brief, our entire civilization just a flicker in cosmic time, our planet a tiny speck in an ocean of space. And yet we have the capacity to wonder about these things, to ask questions about the universe and our place in it, to seek understanding even when that understanding is difficult or incomplete. The edge of the universe reminds us of our limitations, but also of our capabilities. We cannot travel to the edge of the observable universe, and we will almost certainly never leave our own galaxy or even our solar system as a civilization. But we can send our instruments and our observations across billions of light years, and we can reconstruct the history of the cosmos from the faint signals that reach us. We can understand the universe through mathematics and physics, using the language of science to translate observations into knowledge, turning photons into insights and data into comprehension. This is a remarkable achievement, perhaps the greatest achievement of human civilization. This ability to understand the universe at scales far beyond our direct experience. To know about things we can never visit and events that happened billions of years before we existed. The edge of the universe is also a poetic concept, symbolizing the boundary between the known and the unknown, between light and darkness, between understanding and mystery. It reminds us that no matter how much we learn, there will always be more to discover, always new questions to ask, always new horizons to explore. The universe does not give up its secrets easily, and each answer reveals new questions. Each horizon crossed reveals new landscapes beyond. This endless process of discovery and questioning is what keeps science vital and what makes the study of the universe endlessly fascinating. The edge of the universe connects us to the deepest questions humans have asked throughout history. Questions about origins and endings, about existence and meaning, about our place in the grand scheme of things. Different cultures and civilizations have told different stories about creation and the structure of the cosmos. And modern cosmology is the latest chapter in this ancient human quest to understand where we come from and where we are going. The scientific story of the Big Bang and cosmic evolution is a powerful and compelling narrative grounded in observation and mathematical reasoning. But it still leaves many questions unanswered and makes room for wonder and awe at the magnificent complexity and beauty of the universe we inhabit. The eternal mystery. At the edge of the universe, at the boundary of space and time, we encounter the eternal mystery of existence itself. The question of why there is something rather than nothing, why the universe exists at all, and why it has the particular properties it has. These questions may have no scientific answers because they ask about matters beyond the reach of observation and experiment, matters of ultimate causation and fundamental existence that may not be reducible to physical explanation. Science can tell us how the universe began and how it evolved and what its structure is. But it may not be able to tell us why it began or why it has the laws and constants it does, rather than some other laws and constants. These why questions push beyond physics into metaphysics, beyond science into philosophy and perhaps theology. And thoughtful people will continue to disagree about whether such questions are meaningful and whether they have answers. What we can say is that the universe is here, that we are here within it, that we have the capacity to observe and understand it to a remarkable degree, and that this understanding is valuable and beautiful, regardless of whether it answers all possible questions. The edge of the universe is both a physical location, a boundary in space beyond which we cannot see, and a conceptual location, a boundary of human knowledge beyond which lies the unknown and perhaps the unknowable. As we approach this edge, we should feel not frustration at the limits of knowledge, but gratitude for how much we have been able to learn and excitement about how much remains to be discovered. The universe is generous with its wonders, revealing new beauties and new puzzles to each generation of observers, rewarding curiosity and careful observation with insights that transform our understanding of reality. The edge of the universe is not a wall or a barrier, but a horizon, a line that moves as we approach it, always revealing new vistas beyond. And so we continue the journey, generation after generation, pushing the boundary of knowledge farther into the unknown, driven by curiosity and wonder, and the deep human need to understand our place in the cosmos. This journey has no final destination because there is no end to questions we can ask or to the depths of understanding we can seek. But the journey itself is meaningful and worthwhile, a testament to the human spirit and our capacity for reason and imagination. As you drift now toward a sleep, let yourself feel connected to this ancient quest, part of the long chain of humans who have looked up at the night sky and wondered what lies beyond. What mysteries wait at the edge of darkness? What truths remain to be discovered in the depths of space and time? The infinite journey home. Now we come to the end of our journey through the cosmos, returning from the edge of the universe to the comfort of this quiet moment, this peaceful transition into sleep. We have traveled in our minds across billions of light years and billions of years, visiting the most distant galaxies and contemplating the earliest moments of cosmic history. We have stood at the boundary where the observable universe fades into darkness and where knowledge gives way to speculation. We have considered the shape and fate of the universe, the mysterious dark matter and dark energy that dominate its content, the possibility of multiverses and parallel realities, and the deep questions about existence and meaning that arise when we push our understanding to its limits. Throughout this journey, we have discovered that the edge of the universe is not a single boundary, but many different kinds of edges, each marking a different limit to our observations or our understanding. The observable universe extends about 46 billion light years in all directions, defining the region from which light has had time to reach us since the Big Bang. But beyond this horizon, space almost certainly continues, filled with more galaxies we cannot see. The cosmic microwave background marks another kind of edge, the surface of last scattering beyond which we cannot see, with electromagnetic radiation because the early universe was opaque. The cosmic event horizon marks yet another boundary, the distance beyond which galaxies are receding so fast that we will never be able to observe them, no matter how long we wait. And there are edges in time as well. The Big Bang marking the beginning of time itself, according to current theory, and perhaps some distant future moment when the universe reaches a final state or when time itself comes to an end, though this remains speculation. Each of these edges reminds us that we occupy a particular location in space and time, a specific moment in cosmic history from which we can observe only a limited portion of the whole. Our perspective is necessarily limited and incomplete. And yet, from this limited perspective, we have been able to piece together a remarkable understanding of cosmic history and structure. We know that the universe began hot and dense and has been expanding and cooling for nearly 14 billion years. We know that matter formed into structures through gravitational collapse, creating galaxies and stars and planets. We know that stars forge heavy elements in their cores and scatter those elements through space when they die, enriching the universe and making possible the formation of planets and life. We know that we are made of stardust, that every atom in our bodies except hydrogen was created in the core of a star or in a supernova explosion, connecting us intimately to the cosmic processes we have been exploring. The edge of the universe teaches us humility before the vastness of creation and awe at the enormous intricate beauty of the cosmos. It reminds us that we are small and temporary, that our lives are brief flickers in the great span of cosmic time, and that the universe existed for billions of years before us and will continue for billions or trillions of years after we are gone. Yet it also reminds us that we are part of the universe, not separate from it, but woven into its fabric, made of the same matter and energy, governed by the same laws, participants in the same cosmic story. As you rest now and let sleep come gently, carry with you the wonder of this great cosmos, the knowledge that you are connected to everything, from the smallest quantum fluctuation to the largest structures spanning billions of light years. Let yourself feel at home in the universe, not lost in its vastness, but embraced by it, part of something far larger and older and more magnificent than any individual life. The edge of the universe is far away, but you are here at the center of your own observable universe, surrounded by the same cosmic background radiation, made of the same atomic elements, heir to the same history of cosmic evolution that has brought everything into being. Sleep well under these ancient stars. Rest peacefully in this expanding cosmos. And know that the universe that cradles you is filled with wonders beyond counting and mysteries beyond measure. The journey to the edge has shown us both how much we know and how much we have yet to learn. And tomorrow we will wake to continue that eternal quest for understanding. But tonight we rest, content in wonder, at peace in the infinite darkness, dreaming under the light of distant suns. The silence between the stars. As we continue our peaceful drift through understanding, let us pause to consider not what fills the universe, but what separates everything within it. The vast empty spaces that make up most of cosmic reality. When we look at images of galaxies and nebulae, we see bright, beautiful structures glowing with light and color, but these luminous objects occupy only a tiny fraction of space, like scattered islands in an endless ocean. Between the stars within a galaxy lies mostly emptiness, with distances so vast that light takes years to cross from one star to its nearest neighbor. Between galaxies, the emptiness grows even more profound, with millions of light years separating one island universe from the next. And in these intergalactic voids, the density of matter drops to perhaps 1 atom per cubic meter or even less. This means that if you could somehow survive in intergalactic space, floating in the darkness between galaxies, you would be surrounded by the purest vacuum imaginable, with matter so sparse that you might drift for years without encountering a single atom. The emptiness of space is difficult for human minds to grasp because we live our lives surrounded by matter, breathing air that contains trillions of molecules in every cubic inch, walking on solid ground, touching objects that feel substantial and real. In space, especially in the voids between galaxy clusters, matter becomes so rare that it almost ceases to exist in any practical sense, and the universe reveals itself as mostly nothing, with tiny scattered bits of something floating in that nothingness. Yet this emptiness is not truly empty, because it contains fields and forces. The electromagnetic field permeating all space, the gravitational field connecting all masses no matter how distant, and perhaps the dark energy field that drives cosmic acceleration. Space itself has properties and structure even where no matter exists. And quantum mechanics tells us that even the purest vacuum seethes with quantum fluctuations. Virtual particles popping into and out of existence too briefly to be detected, but having real effects on the physics of the universe. The silence of space is absolute, because sound requires matter to travel through. Compression waves moving through air or water or solid material. And where no matter exists, no sound can propagate. An explosion in space makes no sound. A star collapsing creates no noise. Entire galaxies colliding proceed in perfect silence except for the electromagnetic radiation they emit. This silence is profound and peaceful. A quiet so complete that it surpasses any silence we can experience on Earth, where there is always some sound, always some vibration of air or ground carrying information about the world around us. In space between the stars, you would float in silence so pure that you could hear nothing but perhaps the beating of your own heart and the rush of blood through your vessels. Entirely alone with your thoughts in a darkness and quiet that extends in all directions without limit. The emptiness and silence of space can feel lonely or frightening to contemplate, but they can also feel peaceful and liberating. A release from the constant noise and stimulation of daily life. A return to simplicity and stillness. At the edge of the universe, at those vast distances we have been exploring, the silence deepens and the emptiness becomes even more pure, with matter spread so thin and energy so diluted that space approaches the theoretical minimum of existence, hovering just barely above absolute nothingness. Yet even there, in the most remote and empty regions we can observe, the cosmic microwave background fills space with its faint whisper of photons, the afterglow of creation itself, ensuring that no place in the universe is ever truly empty or truly silent. That everywhere is bathed in this ancient light, carrying its message from the beginning of time. Our cosmic address and perspective. Let us now gather ourselves and remember where we stand as we contemplate these vast distances and approach the edge of sleep, recognizing our own location in this immense cosmos we have been exploring. You and I exist on a planet called Earth, the third rock from a medium-sized yellow star we call the Sun, orbiting at a comfortable distance that allows liquid water and therefore life to flourish on our world's surface. Our planet is just one of 8 planets circling this star, along with various dwarf planets, asteroids, comets, and other debris left over from the formation of the solar system 4.5 billion years ago. The Sun itself is just one star among hundreds of billions in the Milky Way galaxy, positioned about halfway out from the galactic center in a minor spiral arm called the Orion Spur, or sometimes the Orion Cygnus arm. We orbit the galactic center at a stately pace, taking about 230 million years to complete one galactic year, meaning that since the Sun formed, it has circled the galaxy only about 20 times. And since complex life arose on Earth, we have completed less than 3 circuits around the galactic center. The Milky Way belongs to a small collection of galaxies called the Local Group, stretching across about 10 million light-years and containing about 50 galaxies. Most of them small dwarf galaxies, but including 3 large spirals: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The Local Group is an outlying member of a much larger structure called the Virgo supercluster, which contains thousands of galaxies spread across about 100 million light-years. And even this supercluster is just one part of the enormous Laniakea supercluster, spanning 500 million light-years and containing about 100,000 galaxies. Our cosmic address extends outward from Earth through these nested structures, each one larger than the last. until we reach the observable universe itself, spanning 90 billion light-years across and containing perhaps 2 trillion galaxies. This is our home on the largest scale. This observable patch of the cosmos within which light has had time to reach us since the Big Bang, and beyond which lies the rest of the universe, stretching away into darkness and mystery. Knowing our cosmic address gives us perspective on our place in the universe, revealing that we are not at the center of anything, but rather occupy an ordinary location in an ordinary galaxy, in an ordinary part of the cosmic web. There is nothing special about our position in space, no privileged viewpoint, no central location from which everything else radiates. This is the cosmological principle, the idea that the universe looks roughly the same from any location, that an observer in any galaxy would see a similar distribution of galaxies stretching away in all directions, with those galaxies showing redshifts proportional to distance. We could be anywhere in the universe and would see approximately the same large-scale structure, the same cosmic expansion, the same cosmic microwave background radiation. This ordinariness is actually profound because it means that the laws of physics we discover here apply everywhere, that the universe is comprehensible and follows consistent rules, that knowledge gained in one location has universal validity. Our ordinary location in an ordinary galaxy teaches us that we are not the center of creation, but rather part of it, woven into the fabric of the cosmos, subject to the same laws and made of the same materials as everything else in the universe. This perspective can be humbling, but also comforting, reminding us that we belong here, that we are not alien to the universe, but native to it, born from stardust and energy, temporary patterns in the eternal flow of matter through space and time. The gift of cosmic perspective. As we approach the final moments of our journey and the gentle embrace of sleep, let us consider what this exploration of the edge of the universe gives us beyond mere facts and knowledge. What gifts of understanding and wisdom we can carry with us into our dreams and into our waking lives. The study of cosmology and the contemplation of cosmic scales changes our perspective on everyday life, helping us see our daily concerns and worries in a broader context that can bring peace and clarity. When we understand that we live on a small planet orbiting an ordinary star, in a galaxy containing billions of other stars, in a universe containing billions of other galaxies, our problems and conflicts and struggles take on different proportions, revealed as temporary and local, rather than cosmic and eternal. This does not make our concerns meaningless or invalid, because we still live our lives at human scales where these things matter deeply. But it can provide perspective and perhaps wisdom, reminding us that the universe is vast and ancient and will continue long after our brief moment has passed. The edge of the universe teaches us about our own edges, the boundaries of our knowledge and our mortality, the limits within which we must work, and the mysteries we must accept. We cannot live forever. We cannot know everything. We cannot travel to the stars or visit the edge of the observable universe. And accepting these limitations is part of being human, part of finding meaning within constraints rather than despite them. The universe shows us beauty and order on every scale, from the quantum to the cosmic, revealing patterns and symmetries and mathematical relationships that suggest some deep underlying unity to all of reality. The same forces that bind atoms together also bind galaxies. The same quantum mechanics that governs electrons also govern the early universe. And this unity means that by studying one aspect of nature, we learn about all aspects. That knowledge is connected and builds upon itself in ways that make the universe increasingly comprehensible. The edge of the universe also teaches us patience and humility, showing us that understanding develops slowly over generations, that questions we cannot answer today may have answers tomorrow, or in 100 years, or never. And that the process of seeking understanding is valuable, even when complete understanding remains elusive. Science has been refining our picture of the universe for centuries, with each generation building on the work of those who came before, correcting errors and adding new observations and developing new theories that explain more with greater precision. This process continues and will continue as long as curious minds ask questions about the cosmos. And we are privileged to live in an era when so much has been learned and when powerful new instruments are revealing the universe at the edge of observability. The cosmic perspective reminds us of our connection to everything. The fact that we are made of recycled stardust, that the atoms in our bodies were forged in stellar cores billions of years ago and have been part of many things before becoming temporarily part of us. We breathe oxygen created by stars. We are built from carbon and nitrogen and calcium and iron, all manufactured in stellar furnaces and scattered through space by supernova explosions. And when we die, these atoms will return to the Earth and eventually to space, continuing their cosmic journey. This material connection to the stars is matched by an energetic connection. The fact that the energy powering our bodies comes ultimately from the sun, captured by plants through photosynthesis and passed through food chains until it reaches us. And that solar energy itself comes from nuclear fusion converting mass into energy, according to Einstein's famous equation. We are solar-powered beings on a solar-powered planet, children of the stars in the most literal sense. And this knowledge can foster a sense of belonging to something greater than ourselves. A participation in cosmic processes that dwarf individual lives, but include us nonetheless. Returning to this moment now, as our journey draws to its gentle close and sleep reaches out to embrace you, let us return from the edge of the universe to this present moment, this peaceful here and now, where you rest in comfort and safety. We have traveled so far in imagination, crossed such vast distances in thought, contemplated mysteries that stretch the mind and concepts that challenge understanding. But now we come back to simplicity, to the immediate reality of your breathing and your heartbeat, the softness of where you lie, the darkness behind your closed eyes. The universe we have explored continues its patient expansion. Galaxies continue their slow dance through space, stars continue to burn, and planets continue their orbits. But these things happen at their own pace, in their own time, without requiring anything from you. You can let go of trying to understand, or remember, or grasp. Can simply allow the knowledge to settle gently, like dust falling through sunlight, landing softly in your mind where it will remain available when you need it. But quiet now, so you can rest. The edge of the universe is infinitely far away, and you are here, safe and still, connected to everything through the atomic bonds that make your body and through the web of causation that links all events across space and time. But separate enough to rest, individual enough to simply be yourself in this moment, without needing to be anything more. Sleep comes naturally, like the expansion of the universe, like the cooling of the cosmic microwave background, like the gradual dimming of stars as they age, processes that unfold without effort or intention, simply following the inherent nature of things. You do not need to make yourself sleep any more than the universe needs to make itself expand. These things happen on their own when conditions are right, when the time has come, when resistance fades and natural processes take over. Feel yourself settling like matter, settling into the gravitational wells created by dark matter, like gas cooling and condensing to form the first stars. Effortless processes guided by fundamental forces, requiring no conscious effort or control, just allowing what wants to happen in its own way and its own time. Your thoughts may drift like cosmic dust on stellar winds, floating freely without direction or purpose. And this is perfectly fine, because sleep does not require focused thoughts or concentrated attention, but rather the opposite. A gentle letting go of focus and attention, a release into randomness and dream. The universe at its largest scales is homogeneous and isotropic, looking the same in all directions with no preferred orientation or special location. And your mind approaching sleep becomes similar, losing its everyday structure and organization, becoming more uniform and undifferentiated as consciousness fades into the peaceful darkness of sleep. At the edge of the universe, we found horizons and boundaries that cannot be crossed. And at the edge of sleep, you find a boundary that you cross each night without effort, the mysterious transition from waking to sleeping that happens in its own time and cannot be forced or hurried. Trust this natural process as you trust that the sun will rise tomorrow and that gravity will continue to hold the earth in its orbit. Trust that sleep will come because it always does, because it is part of the natural rhythm of human life as much as the expansion of the universe is part of the natural evolution of the cosmos. Let the vastness of space and time that we have contemplated serve not to make you feel small and insignificant, but to make you feel cradled and held within something larger, a tiny peaceful point of awareness within an infinite field of being, resting in the gentle darkness as the universe rests in the gentle darkness between galaxies. Everything is as it should be in this moment. You are exactly where you need to be, and sleep approaches on silent feet like ancient starlight crossing the void, taking its time but inevitably arriving, bringing with it the gift of rest and restoration. The edge of the universe watches over you from its impossible distance. The cosmic microwave background bathes you in its ancient photons, and the dark energy that fills all space fills the space around you as well, connecting you to the furthest reaches of creation, even as you rest here in complete stillness and peace. Dream well among the stars, rest deeply in the cosmic night, and know that morning will bring you back to this world refreshed and renewed. But for now, there is only this gentle darkness, this quiet breath, this perfect moment of letting go and drifting softly into sleep.